This video on ionizing radiation safety is to help you and your supervisor address radiation safety in your section. It should be reviewed annually to satisfy initial and refresher radiation safety training. After viewing this tape, please take a few minutes to discuss radiation safety procedures that pertain to your area. With informed workers, responsible supervisors, and an aggressive safety program, we can reach our goal of keeping all exposures to ionizing radiation ALARA, or as low as reasonably achievable. Ionizing radiation is used throughout the Air Force in a multitude of applications. Whether it's used to see inside a body or an aircraft part, ionizing radiation is high energy and must be strictly controlled to prevent or reduce exposures. This type of radiation emission includes high-energy photons like X-rays and gamma rays, as well as particles like alpha, beta, and neutron radiation. Ionizing radiation is just another property of matter in the form of energy release that occurs naturally. Whether it's coming from uranium or underground, rays from the sun, or the cosmos, we are continually throughout our lives being exposed to naturally occurring background radiation. We can't control or limit background exposures. However, there is a lot we can do to control and limit our occupational exposures. Ionizing radiation can be generated by emitters that use large voltages to force electrons to strike a target and release X-rays. The X-rays generated are then filtered and collimated to produce X-rays of desirable strength. Ionizing radiation is also produced by the natural decay of radioactive materials. When radioactive materials decay, they revert to a more stable form and release energy in the form of one or more of the following: gamma rays, alpha particles, beta particles, neutrons, light, and heat. Different radioactive materials have different energy release signatures. Radioactive materials are chosen on what type of energy release is required for the process. For example, a radioactive material called americium-241 is commonly used in smoke detectors and in lantern pods. Americium-241 emits an alpha and gamma radiation when it decays, which meets the required energy signature for the system. It is important to note that materials that are irradiated do not normally become radioactive unless they are subjected to extremely high radiation, as found in nuclear reactions. Most materials that are exposed to ionizing radiation remain essentially unaffected. However, ionizing radiation can and often does damage to cells that are exposed to high enough levels. This type of acute exposure is not likely to be significant unless large doses are received, repeated exposures are experienced, large portions of a body are exposed, and sensitive tissues are exposed. Ionizing can change the DNA structure, producing a mutation. If the DNA is damaged at a certain spot and it can't repair itself, it may cause a tumor or cancer. When a DNA strand is mutated, the cell dies most of the time. Repeated exposures increase the odds that one mutated cell will survive, producing a cancerous growth. Since more exposure equals more risk, all exposures must be minimized. We can minimize our exposures through four main control measures: time, distance, shielding, and contamination control. Time. When working with radiation sources, the more time personnel are exposed to the source, the more radiation exposure personnel will receive. The exposure effects may be unnoticeable or negligible, but the overall dose is always considered cumulative. Therefore, careful steps must be taken to minimize exposure. Steps like rehearsing a radiation procedure, adjusting a source's power output to what is needed, and careful management of on times will prevent unnecessary retakes and reduce the time the source is used. Distance. The most effective method of minimizing radiation exposures is to simply increase the distance between the source and the personnel exposed. The inverse square law applies to radiation emissions, in that the radiation intensities fall off very rapidly as the distance increases. For example, if the distance is doubled, the radiation intensity is reduced by a factor of 4. Obviously, a few feet may make a difference. Steps like keeping personnel as far away from the source as possible, establishing and maintaining controlled areas, and directing beams away from potentially occupied areas are extremely important. Shielding. Any material placed between the source of the radiation and the potentially occupied areas will absorb some of the radiation and thus reduce exposures. In general, the more material used or the denser the material, the more radiation will be absorbed. Shielding is generally required when areas adjacent to the radiation source are potentially occupied. Good shielding begins with the proper design and installation of the shielding. Careful consideration must be followed for renovations to ensure the shielding is not compromised. Shielding, such as collimators, must be used to restrict the beam to just the area of interest. Shielded facilities should be used whenever available, or strict control measures must be followed. Last, simple shielding such as lead aprons must be used when required by the operation. Contamination control. This mainly applies to the use of radioactive materials. When a radioactive source is suspected of being broken or potentially leaking, it should be isolated and the Radiation Safety Officer, or RSO, consulted immediately. Proper hygiene is the easiest and most effective measure to prevent radioactive materials from getting on the skin and clothes and to guard against accidental ingestion. For all ionizing radiation operations, a radiation exposure assessment must be conducted during initial performance of the operation and revalidated annually. This survey is usually conducted by the base RSO, bioenvironmental engineer, or bioenvironmental engineering technician, and involves a detailed review of the operation and a review of the established or proposed safety measures. Surveys are conducted using instruments such as an ionization chamber. Ion chambers are enclosed volumes of air or some other gas with electrodes placed inside to collect ions produced by radiation. By measuring the current, you can measure the relative radiation rate. Geiger-Müller or GM tubes like those commonly found in the ADM 300A RADIACT set can also be used for radiation detection. Radiation measurements are actually energy rates and are usually displayed in micro or milli Roentgens per hour. Measurements are taken where all potential exposures may occur, including any possible public areas. The RSO or qualified technician then uses the measured radiation rates and reported usage rates to determine the maximum worst-case exposure a worker or a member of the public could be exposed to. In strict accordance with Title 10, Code of Federal Regulations, Part 20, Standards of Protection Against Radiation, workers may not be exposed to more than 5 rems or Roentgens equivalent man in a calendar year. Pregnant workers more than 0.5 rem during their pregnancy, and the public may not be exposed to more than 0.1 rem per year. If the RSO determines that excessive exposure exists, engineering controls, personal protective equipment, and administrative controls to reduce the exposure potential may be recommended. Based on the exposure potential, the RSO may decide to place personnel on a monthly or quarterly dosimetry program. Certain jobs require personnel to be automatically placed in a dosimetry program. Pregnant radiation workers are required to be entered into monthly dosimetry. For these personnel, the Base Bioenvironmental Engineering Office will assign thermoluminescent dosimeters, or TLDs, to each individual and collect them on a monthly or quarterly basis. TLDs operate very simply by absorbing the radiation they are exposed to, and later release that information when heated in a TLD reading instrument. By measuring the amount of energy released, comparing it to the amount released by the control badge, and running the information through a computer program, the lab can determine an individual's exposure. The results are sent out either monthly or quarterly on these computer-generated reports. Armstrong listing AL 1499-1 and 1499-2 for each individual. The report details the individual's exposure for the last monitoring period and for the year-to-date exposures. The report also breaks out the exposures to the extremities and specific target organs. At the end of each year, an AF Form 1527 is sent to document the individual's exposure. After the form is signed by the RSO, it is sent to the individual to review. There are several types of badges used depending on the type of operation being performed. A whole-body dosimeter badge is the most common and is always required no matter what other type of dosimeter is worn. The whole-body dosimeter must be clipped on the front of the body, below the shoulders and above the hips, and is always worn underneath any personal protective equipment in use, especially lead aprons. The collar dosimeter is worn on the collar and is required to determine exposures to the head and eyes when a lead apron covers the whole-body dosimeter. A neutron dosimeter is worn flat against the body's midsection, usually with a belt. A ring dosimeter is worn to determine radiation exposures to the hand and forearm, primarily in conjunction with fluoroscopy or for personnel who regularly handle radioactive materials. A dosimeter must never leave the work area and should be stored with the area control badge when not in use. Personnel should never allow the TLD to be exposed to heat and sunlight, as this may affect the readings. For personal monitoring, digital alarm dosimeters or DADs are used. These monitors have small ion chambers incorporated into them. They are usually required for personnel who work around high radiation areas. A digital alarm dosimeter should be used in conjunction with a TLD, but never in lieu of a TLD. It is an important reminder that DADs and TLDs offer no protection for radiation exposures. All the required procedures for maximizing the effectiveness of time, distance, shielding, and contamination control should be spelled out in a unit-specific radiation safety operating instruction. This OI should be concise but cover shop-specific operations, training requirements, protective equipment required, engineering controls, and procedures of what to do if you suspect an overexposure. If during an operation you identify a potential problem, you must do the minimum: cease operations and secure the area. Seek medical assistance if required, contact your supervisor, contact the base RSO. For after-duty hour emergencies, the RSO can usually be contacted through the command post or through the after-hours medical care phone line. Have each individual complete a statement of events including any and all operating parameters, distances, observations, times, and conditions.
Will ionizing radiation hurt my chances for having children?
Ionizing radiation can affect the DNA of a chromosome, as previously discussed. Because most mutations are recessive, chance mutation would only present themselves if the genes from both parents have the same mutation at the same location on a given pair of chromosomes. However unlikely, the effect is cumulative for females, as the eggs are developed at birth and never replace themselves. It is another reason to maintain exposures, ALARA.
Will ionizing radiation affect my pregnancy?
A developing fetus is highly susceptible to ionizing radiation, especially in the first trimester. It is critical that women who suspect that they may be pregnant get a blood test as soon as possible in order to be placed in the Air Force Fetal Protection Program. The program requires the workplace to be evaluated for possible factors that may adversely affect pregnancy. Based on the workplace factors, work restrictions or modifications may be required. Women who require an X-ray are asked and often tested to ensure they are not pregnant.
How do I know if I've been overexposed?
An overexposure is difficult to detect without instrumentation. Most people suspect they are exposed only after they realize a mistake may have been made. A unit left open, a safety device defeated, inadequate area signs, and such. All suspected overexposures must be reported and then investigated.
Where can I go for more information?
Your supervisor, base RSO, or bioenvironmental engineering. They have workplace information and documentation about the radiation exposure potential. Your base should have a specific instruction about radiation and ALARA. For radioactive materials, AFI 40-201, Managing Radioactive Materials in the U.S. Air Force, gives excellent guidance on how we manage our radioactive materials. Some operations that require radioactive materials have specific technical orders governing proper usage and handling. Others are restrictive materials and require a radioactive material permit. Finally, the governing regulation for all radiation exposures is 10 CFR 20. In closing, ionizing radiation is a powerful tool but a potential health hazard. We need not be fearful of it, but we must respect it. With informed workers, responsible supervisors, and an aggressive safety program, we can keep all exposures to ionizing radiation as low as reasonably achievable.